temperature,
and amount of particles,
volume, and pressure of a fluid. PV equals nRT. This is chemistry.
We should actually say gas fluid, not just any fluid, but actually gaseous state, not liquid.
That's true.
Otherwise, maybe they call it the ideal fluids law. The reason is, we talked briefly about this yesterday, gases can do something a lot easier than liquids can.
Alright.
They can change something.
they can change their volume.
Their volume, exactly. They can be compressible or, expand easier to fill spaces.
Wait a second. I'm writing this NR wrong right now.
What are you doing?
Isn't it big?
Calculus. Or
Right.
pre-calculus.
Isn't it big N sub R?
No, that's right.
No,
No,
it's
you're
not
right.
sub-R. It's all those.
You're right.
You got it.
Okay.
That's the chemistry.
You guys remember chemistry? What was P?
Pressure.
What?
Pressure.
B?
Yeah. Volume.
N?
That was the constant.
What's that?
Like constant amount.
Yeah, Boltzmann's. Okay. R?
Molar. Something.
Yeah.
T?
Temperature.
What was R, Rick?
Molar.
Molar?
I don't know.
Oh, mole?
Number of moles, I think, is what he's thinking. Remember, our version here is slightly different.
Number of moles. That was chemistry. Is R the number of moles?
For us, this is the number of gas particles. For that version, it's the number of moles.
Say it in
No,
here.
N is the moles, and R is the constant.
Oh, yeah. These need to be flip-flopped. Doesn't matter. You don't need to know it, this version of it. You need to know this version of it. What's our version? What's P?
Pressure.
No crap. How do we write it in physics?
Big P,
Big P. V.
big V,
N.
Big N.
R.
K sub big B,
K sub B.
Big T.
T. Is N big or little in this case? I don't recall. It's little, right?
Big.
no,
It's
it's
big.
big.
Big. So pressure times volume.
We're using SI units.
Equals number of particles times constant times temperature. Now let's talk about what this means, because it does relate temperature, volume, and pressure of a gas.
And the reason is because in a closed system, what things will not change?
The volume,
Say again?
the volume, the closed system.
Well, no, the volume can change in a closed system. What two things will never change
Oh,
in
the
a closed
number
system?
of particles
Mhm.
and the constant.
The constant, yeah. Those two things will not change in a closed system, meaning that these three can change.
Here we go.
So why, now you said volume couldn't be changed in a closed system before. Don't think of closed so rigidly, okay? A closed system just means sealed off from everything else. It can still expand or contract.
Okay.
Think of like a balloon, okay? It's a closed system, but it has some malleability.
You do know this in part. This actually explains a lot that we know about temperature. If volume is constant. So now for me, I'm thinking about like a balloon. No, not a balloon. Like a pitcher or something, a Tupperware that's closed, you know, where the Tupperware is not going to grow bigger or smaller. So if volume is constant, when T rises, when temperature rises,
The pressure rises.
pressure goes up. Okay? If if P is constant, now we're talking about a balloon. If pressure is constant, when temperature rises, volume rises. That's, you know, when we're talking about a balloon, if you're talking about just a regular amount of air and you heat it up in a balloon, it expands. If you put a balloon in a freezer, it will
Shrink.
yeah.
And that's what keeps pressure constant, because it can expand. If it couldn't expand, pressure would not stay constant.
Right. And so you can't simply say one thing like, if temperature goes up, then pressure will go up. You can't say that. Why?
Because the pressure.
Does the container can expand and the pressure can expand?
Because this is not direct variation. It's not direct proportion. What is it? It's actually termed, we're working on it in Algebra 2. We just introduced it yesterday, Mick. What type of variation is this? Did you do your homework?
Yeah. Joy something.
Joint variation. And what does that mean? It means it involves multiple different inputs and outputs. So it's not like fingers to human beings is direct variation. There are 5 of us. How many fingers are in this room?
50.
50. You have to take it and multiply by 10. You know how many eyes are in this room? There's 10. But with this, you can't just say, if blank goes up, the other's going to go up. Now, the reason we can do it here is because we're basically setting one of these. Well, how many variables do we have right now?
4.
We have 4 because this one is always, this is one of the 20 some odd constants in nature that are just there because they're there because they're there. 6.02 times 10 to the 23rd. Why is that the case? We don't know. Someday we'll ask. What the heck was 6.02 times 10 to the 23rd? Why?
That's moles, right? Avogadro's
That's
number.
Avogadro's
Didn't I
number.
tell you they've actually counted that with precision now? They've actually taken the number of molecules and counted that to within like less than 0.001% accuracy.
Wow.
Avogadro was right. Which is pretty cool.
I always call avocado.
Yeah. That's a fruit.
I know.
But
I haven't seen it the other day.
But yeah, the reason we can do it there is because we're setting one of the constants, or one of the variables to be a constant.
none of those things has to be constant, right? If I add air to a tire, I'm changing the number of particles, right? And so I'm probably increasing pressure also, PSI. If you're talking about just temperature rising again, the number of particles is constant, if this is a closed system. Neither of these has to be constant. Temperature could affect both pressure and volume. And I would argue actually that in a balloon, a hot air balloon, I would think it's a combination of the two. Because the reason the balloon expands in the first place is because pressure is trying to equalize. It equalizes once it's at a larger volume. But nothing of these three, none of them have to be constant. It's not like, okay, whenever you're doing this, one of those things you must choose to be constant. No, none of them have to be constant. That's what Mr. Ernst is talking about with joint variation. The temperature rising can affect both of these in different ways. If it's a something real rigid like a rubber tire, and you raise the temperature, the volume might increase just a tiny bit, but mostly it's going to be pressure, right? Whereas just a regular rubber balloon, if you increase temperature there, it's probably going to be more change in volume because the wall is not so rigid. Make sense? So it doesn't have to be just one or the other, and it's not always the same rate. So why do we care about the ideal gas law? Well, what about the ideal part?
Because isn't it most gases like it applies to this?
Say again?
Like most of the gases apply to this.
It applies most gases.
Yeah, we can apply most gases to this. Yeah, most gases fit in the ideal gas law, even though they're not really ideal. Okay. Remember, ideal situations like the best of all possible worlds. No, think of like frictionless. You know, there's no other variables. There's nothing that could affect it. It's like in a perfect world, ideal. You know, ideally there would be no sin in the world. You know, something like that.
Yeah.
Well, that's not the case. But most real gases will function pretty much like ideal ones, okay? And there's a little bit of play here and there, not enough change to make a difference in this equation for us right now. So it can be modeled, a real gas can be modeled as this, just like how in physics we, often simplify the system. We'll simplify the real gas, which probably is not a pure thing, because think about it, number of particles, a lot of times this would have to do with a single element or something like that. Or something where we know the proportion exactly and there's no impurities. The air we're breathing right now is full of dust. It's not just gas molecules, right? That would make it not ideal. But for our purposes, it will still work as ideal, even though it's really not. So that describes its behavior, that's all. And it works the same way. So let's say now if temperature is constant. So now I can't raise temperature. That means this entire side is locked in place, right? So what's going to happen over here? Between these two, I can either increase pressure or volume, right?
Yeah.
And as increase one, the other will do what?
Decrease.
Right, exactly. They can't both increase if temperature stays the same. Give me an example of that.
If volume increases, the pressure will decrease. If what?
Volume increases, the pressure decreases, or
Yeah.
Do you confuse yourself?
Shut up. Yeah.
let's think about the other way around first, okay? Think of as the volume decreases, the pressure increases. Why would that be the case? That one's easier to think about.
Really?
Yeah, I'll show you.
I don't
T
think
constant
so.
or P and constant.
As volume decreases, pressure increases.
Oh,
Right?
I see.
I'm shifting all the air to somewhere else, so now it's pushing out against that part of the bottom wall. Therefore, if volume increases, the pressure decreases. I'm more equalized now with atmospheric pressure. Nice. You gonna make some balloon animals for us?
Woohoo!
Alright, now, the ideal actually refers to something else. And we talked about this yesterday a little bit with the water tower and the pipes. We said if there was air in the pipes, it could be more easily compressed. Remember that part? Well, the ideal part is assuming it's non-compressible or incompressible.
Did we talk about if temperature's constant?
We just did, yeah.
What about it?
If volume decreases, pressure increases.
And vice versa.
Boom.
Okay, so ideally gases that are not incompressible mean we can't change the density. But in the real world, we can change the density with gases a lot easier than liquids. Is that what I'm doing here? Am I changing the density of the air? No, I'm not pressing enough for that to happen. Okay?
Yeah, too weak.
Yeah, so are you. The air compressor in the basement that we were talking about, when that air compressor compresses air, what is it doing? How can you relate that to this equation? What's going on? What is it changing?
Volume.
No, it's got a tank. So the volume is pretty rigid, because it's in a metal rigid tank.
So the temperature.
Say again?
The temperature.
What about the temperature? The temperature is going to change as a result of something else happening.
We'll talk more about this.
Yeah, we will. Next chapter especially.
Correct.
But real quick here. When you compress air, what are you doing? You're putting more air in the same space, right?
Mm-hmm.
More air means more particles, right? So you're increasing N. Because you're increasing N, what else is increasing?
P.
Say again?
P.
P, right, pressure. Yeah. So as a result, pressure increases because they're inside this rigid tank. Now there's more air molecules and they're bursting to get out. As a result of all that going on, heat is generated too. Now how does that relate? Because that's over here. It has to do with how much pressure there is. So it's kind of the other way around. If temperature is constant, over here, if volume is constant and pressure is rising, the pressure rising can affect, it's like this affects this. It's almost like a chain reaction. Yeah. All right. You want to go with the balloons now, or?
No, it's not done yet.
Okay. What happened to the balloon?
I'm currently adjusting something.
I see. Okay. But for most cases, especially in ideal gases, if it's incompressible, what ideally will not change?
The number of particles.
No.
Well, if it's incompressible.
Yeah. But what if you add particles?
Oh, I see.
This is a tricky one. Uncompressible, meaning that if I can't compress this, what can't I change?
Pressure.
Well, yeah,
You can't change the.
but I also can't change the volume, right?
But you just did.
No, I'm saying, okay, if I couldn't bend this, I couldn't change the volume, right?
Yes.
Yeah. So in the ideal gas, this is usually going to be the case. Usually we're going to assume that volume is constant, even though it's really not completely. That's all. And again, we're talking about confined
Why is
gas,
that
we're
the
talking about
case in the
closed
top,
system.
by the way? We talked about this.
On the what?
What, that top scenario, circle that top scenario. Why is that the case?
Because the particles are moving. And so,
Because the what?
particles are moving faster.
Yeah, this is actually, this kind of exemplifies the definition of what? Remember what you guys had trouble defining last week? We asked what something was, you were all like, well, it's this, and
Oh, temperature.
yes, this almost defines for you temperature. Because, like Anna said, what is temperature actually? Anna never said this. She said it last week maybe, but not today. What is temperature again, guys?
The amount of movement of energy you're saying.
Yeah, what type of energy?
Kinetic.
Yeah, the average kinetic energy of all particles within a substance, if you recall. Now, that makes sense with that top scenario because kinetic energy is completely reliant, AJ, on... Yes, you do. Listen and think. Kinetic energy, AJ, is completely reliant upon movement. See, I told you that you knew. Movement. Well, within this room and within actually this atmosphere currently, the cells are gradually, not the cells, the particles are gradually moving faster and faster. Why?
Because of like the time of day and the sun.
Because it's 8:40 a.m. So,
The sun is out longer.
the sun sun is just getting out right now. And
It's heating.
yeah, this morning it was actually there was an article in the Herald. They were worried because the apple orchards are blooming right now. And this morning, well, on Good Friday morning, it was 28 degrees. I mean, only for probably, I think they said like 45 minutes did it go below freezing. But that's long enough. This morning, again, it was like 31.
I covered up one of my small trees at home so that
Yeah.
it wouldn't.
And so they were worried about, it's not going to kill the tree or the plant even. However, if they're blossoming, it'll kill the blossoms.
Well, my small tree is literally about 6 inches high, and it's basically just a couple of very thin twigs, and there's a possibility a frost could kill that, which is why I covered it up.
But I'm talking,
Yeah, big trees no frost.
Right, with the apple orchards and even the, there you often hear about orange trees in Florida.
Yeah.
If it's too cold in the fall, that the orange crop will be ruined for the year.
And a lot of times what they'll do there is they'll have all these big kerosene lamps and like propane burners out in the middle of the orange grove so that they can actually
Get those
try to
particles
keep
moving.
the outside. Yeah.
Get those particles moving. But yeah, so throughout the day, the particles are moving faster and faster. So does the pressure increase?
Not really. There's too much, because, there's too much space for it to have much effect on them.
Too much space for it to have much
What's
of
the volume?
The volume
It
is
can't
set?
take up the space.
The volume is set or no?
For the most part, yeah.
Of our atmosphere, sure. But you have to think about the fact that, you have to think on a large scale. If you're thinking about it as an atmosphere, we're only a small part of that whole atmosphere. And so, although the heat is concentrated in this area, it's dissipating everywhere else, if that makes sense.
Yeah.
And so, are we a set volume? Per se, I would argue no, especially when you're only fluctuating by 30 degrees in a day. It's not going to affect it that much.
There is actually a measurable distance in the height of the atmosphere during the day. It's actually higher.
It is higher.
I mean, it'd be something like this. Here's the sunlit side, here's the night side.
Huh.
Okay. The atmosphere on the day side is thicker.
So
Because
Mr.
the
Gaspar
particles
would
move
argue that yes, there is a slightly higher, well no, there's not a slightly higher pressure, but rather a slightly higher volume.
Well, I'd argue there's both. Higher pressure and higher. No.
No.
Yeah, just higher pressure.
You would know.
There's just higher volume.
You would argue, yeah, just a higher volume. That the atmosphere actually does bend out a little bit.
Well, this should make sense too, because what does heat do? Does it sink or rise? It rises because it's under less pressure. You've lowered the density because the particles are farther apart. By doing that, how do you relate pressure to density? We can do that, right?
The lower the density, the higher pressure? No, the
No.
lower pressure.
Why
Yeah,
does
lower
heat
pressure, lower
rise?
density.
Think about it relative to this.
Because
Really, what we should say is a heated substance, because heat itself is not. Really
Yeah, heated substance rise. Think about it in terms of this. And the fact that what we said often holds true is that one of these, it's not at a constant, but typically it would generally
It's very close to being.
It's very close to being at a constant. And what is that usually? What is usually the case? If it wasn't the case, your ears would hurt, I'll tell you that.
the
What is typically at a constant?
pressure?
Pressure. Pressure is almost always at a constant.
You're talking about in the atmosphere.
Yes, I'm talking about here on the atmosphere.
Okay.
It takes a force for us to change a pressure. What type of force?
Heat or
Heat is not a force.
right? If heat changes,
I would argue that heat can indeed impart a force.
Heat can impart a force, sure, but heat in itself is not a force. But Anna, if you think about it,
Where does heat come from?
if we heat, if you go outside and it's freezing, what's going to happen to your hands?
they get
Thank you. They are going to shrink. They're going to get
Oh,
smaller.
okay, yeah.
And the pressure in them is not going to change. And then you go into a sauna and you let your skin breathe because it's healthy for you or whatever. You're going to be slightly, like your body, although you're not going to see it, your skin, your pores are going to open up, you're going to be a little bit bloated, a little bit bigger than you are when it's cold. The pressure is not changing at all. Because what two things are? Temperature is changing and volume. Your body's going, or your body's going, okay? Volume is changing with temperature. Pressure rarely changes. It takes a force to change pressure. Like, if you think about a trash compactor, that's a force that's changing pressure. You know, if you put a bunch of water in a trash compactor, it would struggle once it got to the level of the water because water is very hard to compress.
Assuming the water wouldn't just squeeze out somewhere. If it was a closed system, yeah, it would.
Yeah, but it takes a literal physical force to change pressure. So that is almost always at a constant. Now, why does a heated substance rise?
Because it wants to be free.
Oh, come on.
Come on, people.
Physics terms.
Think.
Boy.
Silly.
He's right, though.
No, yes, no. No, not really. Yes, a little.
It changes the buoyancy.
It changes the buoyancy. Why? What happens with a heated substance? Let's just work from the basics.
Density.
Particles.
Yes, Mick, you're correct. Mick said density, but now I want to work through it. What happens with heated substance?
What do they want?
The particles move.
By heating them, you were giving them
Movement.
Kinetic energy.
energy.
You're giving them kinetic energy. Particles move faster. Hence,
More friction.
So let's go with more collisions.
More pressure. More pressure.
no, we just said pressure rarely, if ever, changes. We would need to, if it's going to be more pressure, that means we are using a force to contain it in a set volume. If temperature increases,
The volume is.
more than likely volume increases. If volume increases,
There's.
Mick,
Density change.
density changes. If volume increases and mass stays the same, then density. If volume increases, bear with me guys, picture yourself as being really fat and your mass didn't change, would you float?
No.
Oh,
If
come
mass
on, watch
didn't
cartoons.
Sure. Yeah.
If volume
That's when,
increases
some
and mass
I
Jack
see.
Full there. They
Okay.
start
volume
I can see
increases
what
and
you're
mass
saying.
doesn't change. Volume increases and your mass stays the same. Then your density
Decreases.
decreases by a ton and hence heat rises because the least dense thing wants to go to the top.
And a balloon's a perfect example of that. When the balloon is shriveled up and has no air inside, you drop it and it just falls, right? Or if you hit it, it just, stops on the table. But if it's full of air, it's going to bounce around a little bit.
Yeah.
Okay, kind of like you being full of air, you being bloated, huge. You guys seriously never watched a cartoon or something where
Yeah.
something was,
Yeah, like
full of
Harry
air, full of
Potter
air.
and the woman blew up and she floated around.
Oh.
It's in one of the movies. I can't remember which
I don't know about that
one. Yeah, thank you.
one. Okay, I'll take the report. Anyway, yeah.
Ah. Wow, it's been too long.
But what we're saying though is ideally, or nothing is truly ideal, so really all three of these things can change. They can all change in the same system.
Yeah.
That's all. I don't think we actually do any equations with this, do we? Yeah, we'll have to do a couple examples here.
Yeah.
Look at the example of page 340. Pure helium gas is contained in, okay, so it's pure, so we're saying something's ideal here. In a leak-proof, yeah, that's ideal too. Cylinder containing a movable piston, as shown in figure 917. The initial volume, pressure, and temperature are certain things. If the gas is rapidly compressed and pressure increases, find the temperature. So, by the gas being compressed, what's changing?
The volume.
Volume is changing, right. And as a result, pressure is increasing,
Yeah.
right? And that goes along with these being inversely proportional, right? One goes down, the other goes up.
Yeah.
But the temperature is also increasing. Why?
Because
All those molecules are now in a smaller space, therefore they
Collide, causing
Yeah.
more pressure.
This is kind of tricky because what we're doing is the temperature is going to raise because they're going to collide more, they're bouncing around more. Where did they get the extra kinetic energy from? If the temperature is an outcome, where does the energy come from in the first place to make the temperature increase?
well, I mean, it came from a larger volume, so when
Large volume being compressed to smaller volume,
and so
but it's still the same number of molecules.
exactly, and so there's less space for them to move, I guess.
So just by having less space to move around, you said it right there. What kind of energy do they have less of if they're compressed?
Kinetic.
Just because they can't move, yeah. Since they can't move as much, they're going to let off some of the heat, some of the energy as heat instead of movement. They would prefer to move, but they can't, so they generate heat. It's kind of like when I'm going to relate to space again because I always do. We talk about black holes, things going into black holes. Eventually, something getting pulled into a black hole is going to reach the speed of light as it goes in, right? And then it can't accelerate anymore. But if it's getting closer to the center of the black hole, it's still gaining energy, right? It can't gain kinetic energy anymore, though. You get the idea. Usually GPE, gravitational potential, is converted into kinetic. But once you reach, that's like the ultimate terminal velocity. Once you reach the speed of light, you can't convert anything else into kinetic energy. So where does that converted potential energy go?
Into heat, then.
Into heat, yeah. Heat is like the pressure release. Well, I don't want to say pressure release valve. We're talking about pressure. Heat is like the last outlet. Okay. If something can't move more, it's going to generate heat instead, and that's what's going on. It is the same idea of an old-fashioned incandescent light bulb. You run electric current, which is moving electrons basically through this filament, which is a high resistance. In other words, it can't let many electrons through. So there's a backup of electrons. It's like a bottleneck on a freeway or something. 5, 6 lanes all split into one. What happens? Traffic jam, right? It's a traffic jam of electrons. Well, rather than all trying to get through because they know they can't, it's not just like a fluid where they can just speed faster through the channel. It's only wide enough for one electron. So instead, the extra electrons just kind of vibrate around and generate heat instead to let off that excess moving energy they can't use. And that heat makes the light bulb glow and you get the light. So, and that's why the old incandescent ones are so inefficient, because they are based on heat making things glow.
Oh, my light bulb in my room is so bad. You turn it on, you just feel the heat instantly. It's so
Yeah, like halogen or xenon bulbs, yeah, those are super hot. Although those are actually more efficient than incandescent.
Oh, really?
Anyway, yeah.
Interesting.
And the halogen and xenon, those are gases. Those are noble gases inside. Anyway, alright, so this sample problem. All we're doing is plugging stuff in here. And what we want to do is create a proportion. Alright, because basically what are the three things that are capable of changing in here? In a closed system where no gas particles are being added.
Temperature, volume, and pressure.
Temperature, yeah. So temperature is the oddball here because it's on this side. We want to get temperature on the same side. Okay? So we'll divide. Now we have that on one side equals our constant. Okay? This is going to be a constant before and after. Right? Because even after I compress it, I haven't added or taken away any gas molecules, and the constant sure didn't change. So, that means then that it's an initial slash final situation, okay? Initial PV and T is going to equal the final PV and T.
Okay.
We don't even care about our number of particles or our constant in this case.
So what should happen?
One more should sit on top.
One should sit on top.
Which
right?
one's the one?
This field.
Oh, yeah, I can tell.
Considerable. Considerable difference in temperature, right?
Mm-hmm.
I mean, to the point where you can feel this glass is starting to get softer
Yeah.
because it's warm. So, if I pour this in, it should sit on top.
Yeah.
Shit.
What?
Well, here,
What do you mean?
What is that? Great water.
this way.
What
They're
did you
both
say?
water, right?
They're both water.
Oh, okay.
This is red water. This is clear water.
Yeah. So yeah.
How do you keep water from mixing? That's the
Go
problem.
ahead, put it on the bottom. That's my point. Why does it not stay? In fact, there's two things that are in our favor as to why the clear water should sit on top of the red water. What, by definition, has to be the case relative to the red water and the clear water? The red water must be more dense. Why?
It's cooler, and it has more stuff.
It has more stuff. It has more stuff in it. So the red water should sit on the bottom, but it doesn't. Why? This is more probably what you learned last year, but
Because it's, I mean, it has to mix together, kind of. It's the same substance.
it's kind of what we were talking about with yeah, it is the exact same substance. What we're talking about with ocean. It still mixes.
Yeah. Well, plus I plopped it in.
Correct. We're talking about with the ocean. The water in itself, I mean, with heat, what is heat? What is temperature again?
Yeah.
What not just. There's one word you're missing.
Movement of.
No, there's one word that starts with an A that you're moving. That you're moving, that you're missing. A blank kinetic energy within a substance. Blank kinetic energy of the particles within a substance. The blank. A word. Average. Average kinetic energy of the particles within a substance. And so this basically illustrates the fact that, number one, although it is an average, that in the end, those, and this will make a little bit more sense when we get to it next chapter, but those particles that are hot want to share the energy that they have with the particles that are cold. And hence, it's not going to stay separated like that. It works so much better with salad dressing is a perfect example. You know, when you let salad dressing sit, it is very much layered because density in the end is what is going to factor out. Well, the problem is this density is exactly the same. You know, so if I chucked the water full of dye, maybe it would have worked, but I still don't think so. It has an inherent will to mix with itself.
If we had a larger tank and we had a way to suddenly combine the two samples of water without causing any turbulence or any movement, then we could see convection kind of take over, and we'd see the red sinking or the white stain.
You would. I was a bartender for a while, and have you guys ever heard of a black and tan?
Yes.
A black and tan is it's a beer. Well, it's two beers that they mix. So Guinness is very dense and thick and dark, and then there's either black and tan or black and blue. And you have like Blue Moon, which is a light Belgian, much less dense beer, and some people like to mix them. Well, the reason that they like it is because it looks really cool. You have the dark beer that sits on the bottom and the light beer that comes up top, and they stay separated. But the problem is you can't just pull on the tap and let the beer go in, and on the second one just pull on the tap and let the beer go in. you actually have to
we should.
use a spoon. So the beer comes out of the tap and it has to go onto the spoon. Because you have to kill some of its velocity downwards. Because like Mr. Gottschalk said, if he goes ploop, it's causing an inherent mix. And then, I mean, if you do that, sometimes you'll actually get the particles to bond with one another. And that's the case with this beer thing too. Once they bonded, they never separated. So if you screwed it up, you had to dump it out, and then they got angry. So you had to do it carefully, otherwise it'll mix. Similar here, you know, with salt and water, you can get salt to sit all the way on the bottom. You could be drinking a cup of salt water, and it wouldn't even taste that bad. You could have a truckload of salt on the bottom if you were very careful about it, because they wouldn't mix. They have
Not even that. I mean, salt needs agitation to mix, so you can just dump it in anyway, and it'd still be fine.
Yeah, they have no reason to mix because salt is more dense than water, so it wants to sink all the way to the bottom. You know.
But once you mix it and you do get it to dissolve, they're very hard to separate.
Right. Correct. Almost impossible. Really, the only way to separate salt with water after it's dissolved is to evaporate and then recondense. You know. So why is the ocean salty? We wouldn't talk about this soon enough.
I think there are currents underneath.
There what?
Currents of the water.
Oh yeah, sure there are currents, but what you guys know why water has its saltiness? Any ideas?
I know. I think it has to do with chemistry.
It does. No ideas? What's salt? NaCl, is that right?
Could be KCl, could be a bunch of
KCl.
different stuff. Table salt is NaCl, yeah.
There's many different parts. Yeah, salt can be many different things. Chloride, I believe, is an integral part in all of them.
Yeah.
Right?
I think you have to have one of those. It has to do with the columns of the periodic table. You have one with an extra electron, one with a deficiency electron.
But I think chloride is necessary in all salt, isn't it?
I don't know. That's what I want to check. I just saw a Nova episode on this, which is why I'm wondering. This is awesome. I was, my wife was watching, what was it? Chopped on the Food Channel. It's kind of a cool show. Watch it sometime. I'm sick of it. We watch it so much. But I fell asleep during it. When I woke up, she was asleep. But after Chopped had gone off, the DVR had automatically switched to Nova because I was taping. I automatically tape all new episodes of Nova, whether I want to watch them or not, and I decide later. And it comes on, they're talking about the periodic table, and it was, I mean, usually I'm not all that interested in chemistry stuff. It's kind of cool, but this is a really good show. It talked about, well, they were talking about salt and what happens with it. And the reason is the periodic table.
Have chloride.
You have what?
It does not require chloride.
All it requires is
one of the first two.
Yeah, here's your periodic table. Basically, your chlorides and stuff are in this column here, which means they're lacking one electron, and all your like the calcium or the whatever.
What are
is
they
over
called?
here.
Alkaline. No.
Alkali. Yeah.
Alkaline metals is right here.
No, this
No,
is
it
alkali
isn't.
metals.
It's in the first two.
Yeah, alkaline and alkaline.
Have one extra
what are these?
electron.
Those are.
Noble gases. Noble gases.
No,
No, noble gas is on the
gases,
very
Yeah,
last
it's
one.
there.
Yeah, I know. That's what I was saying. I said right here, and I said noble gases, and I changed it. I got nervous.
What page is the periodic table on again?
7 something.
I think it's 8 something.
8 something. That's what I said.
Really narrows it down.
Wow.
Here we go. 9
9
something.
something. I knew that.
Okay, it's group 2. That helps a lot. Oh, okay, no, it is group 1. It's the first group over here, which makes sense. Because they only got one out of the possible. Wait. Yeah, one extra electron. That's this end column here. I don't know the name of that column though. They're not a very good periodic table in that book. That's the problem.
environmental chemistry.
964.
Thanks.
Well, all right. So anyway, salt is there. Well, why salt? Why is the ocean salty? What gives the ocean its salt?
God.
God, no, because it would eventually run out, wouldn't it? Because doesn't part of the ocean evaporate every single day? You know,
Yeah, so wouldn't you
wouldn't it all come back?
right? But then what would cause it to mix? You know, eventually
The
we're
movements, as Anna said. The
What?
movement of the ocean.
and the fishes?
the fishes, fish,
The octopi.
the octopi. So, but why? Like, do you think God just said, and let there be water, and let a majority of the water be salty,
So we wouldn't drink it all up.
so we don't drink it all up? And it was good. I don't think that's how it went.
It could have.
Actually, I don't know. Do you think God, I bet you the initial bodies of water were all fresh? Probably, when He created them.
And
Yeah,
then
well,
what?
even
Once they
from
came in the world,
a
it's just like,
geological
nope, salty.
standpoint, yeah. And they would become saltier as erosion would cause things to run into them and dissolve.
Mr. Gotchard's giving you good clues. But why is the Dead Sea saltier than everything else? You
Is
know?
it a really low elevation?
There's all
It is at a low elevation.
crap that goes into it.
Crap. People crap in the Dead Sea, and we all know that crap turns into salt. So that's gotta be it.
Like from erosion.
Erosion, what about
All that rocks and
it?
stuff.
Well, think about it. What do we have here?
It's a lot. I mean, like, that would have to be a lot of erosion to keep it going then.
Well, yeah, erosion happens all the time.
Yeah, but I mean, it's only on.
How about the flood?
Oh, mixed up.
God.
There's a perfect example for how all the water got salty. It was only salty here or there. Well, plus, think of what the water is over then.
Where's it?
It's over land, right? And
Yeah.
anytime water's over land, the water's going to dissolve stuff from the land. Just like the reason a mud puddle isn't clear is because the water has some dissolved particles and minerals from that mud within it. Not just sediment, but actually stuff that's dissolved.
Yeah.
Well, if you look at the particles that we're talking about, calcium is a big one, magnesium. Both calcium and magnesium are very much involved in a bunch of these rocks that Mr. Gottschalk has over here.
And there's, yeah, that's true.
You know, like there are a lot of rocks that have magnesium and calcium as a part of their chemical makeup. And so when it erodes, it comes within, you know, the water. And the particles, when they erode, it's not like we're talking about big chunks falling off. You know, we're talking about sand and even smaller. You know, particles that are getting rubbed and it's eroding into the water. That's essentially what is keeping our oceans salty, is the erosion that's there. And like Mr. Gottschalk said, the flood is a perfect example of what would have initially caused the oceans to become salty. Because, are you thinking erosion? I'm thinking, holy crap, a ton of erosion.
Erosion and dissolution, how do you say it? Dissolving stuff.
Yeah, right. Dissolving of particles. Now, you know, if you think is there salt that's coming from the bottom of the ocean? Yeah, probably. It depends on what surface it is on the bottom.
There's rock down there, yeah.
Right, there's rock down there. I mean, mud's not going to cause salt, but you know, a lot of
There's some salt in mud.
a lot of the, what is it? Not the mantle, but the
crust.
what's the shallow part on the edge of the ocean?
The continental shelf.
The shelf, right. Much of that shelf is hard rock. Stuff that's going to involve particles that have calcium, magnesium, and some of these
Well,
other...
just all the rivers running from everywhere on the land, you know.
True.
That run in there. And the other reason it stays salty is because of water freezing. When water freezes, it drops the salt. If you go and lick an iceberg, it's not going to taste salty. Okay? when the iceberg froze, the salt is, I shouldn't say an iceberg, is actually breaking off a freshwater glacier. But sea ice in the Arctic Ocean in the winter, that sea ice is not salty. The ocean underneath is super salty because the water freezes and leaves the salt behind. So that what liquid is left becomes saltier.
Are you sure the ice isn't salty? I thought it was.
It's not as salty as the water, I know
That
that.
is salty.
Yeah, there's some. I'm pretty.
There are some salt particles that are trapped with it.
Because
But it's not
basically,
really as salty as the water.
basically I don't know if you guys talked about this in chemistry, but essentially the water particles are like, they're, for lack of a better term, they're hugging the salt. They trap the salt and dissolve the salt within. So it's no longer H2O and NaCl.
Mm-hmm.
It is a completely new compound.
No, it's just, well, that goes into chemistry too. I mean, you're not changing the chemical nature of water.
It's just not.
But you're
pure
now, right, you're now,
They're inseparable, that's all.
correct,
Without adding a lot of energy to the system.
right, aka, yeah, dissolving and then recondensing. But yeah, basically our oceans are salty because of the particles. Now, why aren't our lakes salty? Gosh, Lake Michigan has been sitting there rubbing water up against rock for hundreds of years.
Geological theory says the Great Lakes are about 12,000 years old. Obviously, that's inconsistent with a young Earth creation. But if it were 12,000 years, why isn't there enough time for salt water to happen?
Because they're so big.
Oceans are decently big too.
Yeah, but I mean.
I would argue they're a little bigger yet than the Great Lakes.
What about the Great Salt Lake?
This is true.
Yeah.
I don't know, because
The reason is because it sits over salty land. That's why it's salty.
Yeah.
They think that whole area used to be, the salt flats out there, they think that used to be a shallow inland sea way back, however many millions of years ago, whatever.
But I mean, what are some ideas that come to mind?
Where did the Great Lakes come from? In a geological theory, anyone know where the Great Lakes come from? You do or don't?
Okay. Where did the Great Lakes come from? Where did all of Wisconsin's 1 million, or Minnesota's land of 1,000 lakes come from?
All those, yeah, they tell
10,000
us moraines and stuff and things
That's
like
what-
that. What are those all features?
That's
of?
what Minnesota is claimed to be. The land
Used to
of
be on
10
the license plates.
land of 10,000 lakes. Probably almost accurate. Where do they come from? You guys don't know, really?
No.
Springs.
Did some guy was just like, "Look, I made some freaking lakes," and you have a big shovel, and for a long time just started thinking, no, there are man-made lakes,
Yeah.
It's from a very powerful process of.
but the Great Lakes are a little big. What got rid of the dinosaurs? Possibly,
Flood.
maybe.
Meteor.
Other ideas. Meteor, doubtful.
Chicxulub meteor.
Volcano.
Doubtful. Volcano, probably not.
Earthquake.
Come on, the most reasonable explanation for the
Temperature
dinosaurs.
change.
Temperature change. They call it the
Ice Age.
Ice Age. What happened during the Ice Age?
Everything froze.
Glaciers.
Everything's
Glaciers.
And so
Most of the
all
lakes.
melted and
They
all
say
saying,
that the Great Lakes were carved out, the depressions were carved out by advancing glaciers, because glaciers carry rock and stuff with them. You scrape the bottom and erode the bottom of the, whatever rock is underneath it. And then, when the Ice Age ended and the Earth warmed up, all the ice that was left over melted and then sat there. And it has no outlet, so it doesn't run out to the sea, at least not
No.
fast.
Does that make sense?
yeah.
And that's probably I mean, from a scientific standpoint, that probably makes the most sense. Because, like, for example, Lake Superior is like, I want to say it's like 600, 700 feet deep,
I think it's 900.
900 feet deep at its deepest point.
It's just the deepest Great Lake.
And so to say that any other, I mean, set aside God saying, and let there be 5 Great Lakes, set aside that, any other explanation as to why there's an enormous hole in the ground. And the reason...
Well, you also think about...
You have to think about the floor of the Great Lakes. What do you think the floor of the Great Lakes is like? What's that?
Rock.
Rock? Solid rock?
No, it's
Pebble?
all muddy.
Muddy?
It's all muddy and silty now, yeah.
Right. Most of it is
That
not
organic stuff.
a solid rock.
But the other thing is, that we're ignoring here that you have to think about, I mean, it could be super salty rock on the bottom for all I care. The lakes are still going to be fresh. Why? Because the water is constantly being diluted with more fresh water. From where?
The sky.
Rain and melting snow in the springtime, right? Yeah, which are both sources of fresh water. So even if it were a little salty, it's constantly being diluted, and then whatever overflow is spilling over, St. Lawrence Seaway, eventually getting out to.
I'm still
the
not
ocean.
convinced, though.
What, that you can dilute it?
No. In my estimation, the difference is in the Great Lakes and the ocean is not that much, as far as a causing of salt versus fresh.
I don't know what you mean.
Well, the ocean, we're saying that the reason that it's salty is because of erosion. Well, there's erosion in the Great Lakes. And we're saying that the reason that the Great Lakes is fresh is because it also gets resupplied with fresh water.
Right,
But so do the oceans. And also,
But
melting snow, so do the oceans.
But wait a second, okay? As water can leave the Great Lakes, right?
Can it?
And flow down to the oceans.
Sure.
Okay? Can water leave the oceans and flow down somewhere else? No. So whatever gets to the ocean is going to stay there. The salt can't get out of the ocean once it's there. You know what I mean? Once it's there, it just sits there. And more salty or fresh water can go into it, but the stuff that's in the ocean there, it can't go to some other basin somewhere else.
So,
the Great Lakes have a lower level.
No, the
that
Great
they can
Lakes
go
have
to.
a higher level.
No, they can go to a lower level. That's what I mean. The Great
So-
Lakes are higher. Some of that excess spills over to the oceans. Once it gets to the oceans, there's nowhere else to go.
So what would you say about the elevation of the Great Salt Lake that you are so versed in, Sunil Jamal?
Low elevation.
Why?
There's so much salt you can't escape. The ground everywhere is salty.
Well, chances are, yeah, everywhere is salty, but because of what Mr. Gottschalk just said, one would think that any body of salt water that is not an ocean or a sea would have to be below sea level. Did you follow his argument?
Yeah.
That essentially a good part of the reason that the oceans are salty is that once it goes into the ocean is basically like our dumping ground for water. Once it goes into the ocean, it's not coming out. There's no rivers that are fed by ocean water.
The water will come out by evaporation, but the salt is stuck
Does
there.
that make sense? The ocean doesn't flow anywhere. Everything flows into the ocean, so it's basically like our dumping grounds. Well, once salt gets into it, water can evaporate, but it leaves the salt. All of our freshwater lakes and rivers are being fed from water and dumping all of the water. Basically, I mean, you guys know the water cycle. I mean, basically, it all ends up eventually in the ocean. And then it all evaporates and ends up back everywhere. But the ocean is the last place that it is before, well, majority of it, before it evaporates, which makes sense why the salt all ends up there. Would you say that our oceans are getting increasingly saltier?
Yeah.
Yeah, probably little by little. There's a crap ton of water.
Yeah, I think actually they're saying that the glaciers, like polar glaciers, are melting faster than the salt is being replenished, so actually they're getting a little bit less salty.
Less
That's
salty.
good.
Because like the Greenland and the Antarctic glaciers melting.
Yeah.
But going back to the Salt Lake, what does the Salt Lake empty into?
Nothing.
Nothing, exactly.
Right.
The Great Lakes can empty, Salt
Yeah.
Lake cannot.
And
Also,
so,
the Salt Lake gets smaller each year.
Evaporation, heat.
because it's out in that, and that's another reason that it gets saltier and saltier. Eventually, it's not going to be the Great Salt Lake. It's going to be the Great Salt.
And it's surrounded by, it's called the Bonneville Salt Flats,
It has no
right?
water.
You've heard of the Bonneville Salt Flats?
Yeah, it's insane. It's
Yeah.
everywhere.
The Salt Flats is like this area of thousands of square miles. I mean, you can literally drive for 300 miles in one direction without ever going up or down more than like a foot or two.
And that's where they tested. If you guys remember,
They test like supersonic cars.
we
and
watched
stuff,
a video of like the fastest car. Like when we were talking about acceleration, we watched a car that accelerated from like 0. It was on the MythBusters. That's where they did it, in the Salt Flats.
Because there's no
Because it's
vegetation, there's
flat.
no trees, because they can't grow on salt, and everything's just
And it's because
It's almost like concrete.
not bad on hard cars.
That's incorrect.
Wrong. No. The
Salt
dust-
is terrible on
No,
cars.
but it's not bad for those cars because they're racing them. That's why they don't race them on lake beds as much. They do in
Because
California.
why?
It's because the dust will get up into the engine of cars and the salt can be easier.
I can
to
see
go
that.
for cars.
No, well, yeah, I guess the salt really doesn't do damage until it's combined with the rest of the stuff. Salt
As far
is
as
terrible.
rust goes.
Salt is terrible for cars.
I
and
know
rust.
that, but I mean, like, that's why they race them on the salt.
Within engines. Yeah, it's interesting. It's interesting.
So none of this argument has any bearing on the test, just so you know.
Yeah,
But it's fun to talk about.
it is. It is.
But
Actually, we're pretty well done with the idea. I guess.
yeah, all I was getting to over here was because these two things will not change, we have an initial and final situation. Okay? And it's just more proportions. That's all there is to it.
Check the balloon.
Why do we need to give review questions, I think? What is he doing?
Checking his balloon.
Oh, he probably put it in the freezer. But what he didn't think about is by the time he brings it back in here, it'll probably be pretty much expanded again. So we should probably follow him in there.
Really?
Yeah. Hold on a second. Let me just make sure.
Do not put this in there. Because I get stuff in my hair all the time. Just
Air is a very poor. Air is a very poor conductor of heat, so it's taking a long time to cool down.
Yeah,
That's why your freezer's more efficient when it's full of more stuff.
a reasonably high specific heat.
What low?
Low. High.
Air?
Yeah, it takes a lot of energy to change its temperature.
No, it doesn't. But there's no good way to impart the energy.
Poor conductor, you're right. Yeah,
All right.
yeah.
That's all right. Review questions, page 343.
340.
The other morning,
40.
this was about a month ago, Mr. Gottschalk, I left a water bottle in the truck, and it was right around freezing, and I did the, it turned to ice.
Did it work? Awesome.
Yeah, it's
I love that. That's one of my
I've
favorite
done that.
experiments.
It turned into ice?
I'm
Yeah.
taking
That's awesome.
something out of the
Because-
freezer. I saw it in the freezer and it was liquid, and as soon as I grabbed it, the whole thing froze.
Yeah, we call it super cooling. The water's been cooled below freezing
I didn't
point,
know
but it
that.
hasn't frozen because there's no crystalline structure for it to attach to.
That and well, yes, right. Latent
It's
heat,
really
latent heat as well, which we'll talk about. It's
I will
possible
find
that it is right at the right temperature. You have about a half hour of time, or
Yeah, it will.
when you put it in a freezer.
It'll start freezing all by itself once it gets cold enough. But I mean, super cooling is how we get rain in clouds. All the rain we get here in this climate comes from snow that melts on the way down. Everything, or ice. The clouds are about
Chilly.
10 degrees below 0 Fahrenheit, and the water, they're made of water droplets, not ice crystals. The water is cooled to 40 degrees below the freezing point of fresh water because it doesn't have what's called a freezing nuclei. It needs something to attach to freeze, something to latch onto, something with a crystalline structure just like ice. And if that's not there, it can't freeze. And once one or two of them are there, they all kind of latch on, and that explains the water bottle, because if you look carefully what's going on there, you'll notice that all the crystals kind of go from one place and kind of branch out in the water bottle, and that's what happens up there. Once there's a couple freezing nuclei, all the water droplets attach on it, make a giant snowflake, which then, on the way down, melts into water. We get rain. That's why the rain's cold.
Yeah, that is why rain is cold.
That's cool.
All right, review questions. 1 through 5, 10 through 12, 18 and 16 through 19, 20. No, yeah, 25, 31, 32, 34, and I think that's it.
We're right on the board.
Yeah, I will. I think we're doing, 36 also. Alright. That's it. We can't test on Friday yet, can we?
I'm not gonna be here on Friday.
You're not going to be here?
I'm going to a college visit.
Got it. Are you going to be here?
Yeah, I'll leave it.
Hey!
What should we do?
First time ever.
Test Monday or test Friday or what?
Monday.
I hate to have a test Monday, but
I don't care. We'll do it Monday.
Alright.
I think they'd be more prepared for it Monday than they would Friday.
it's better than giving my earth science students a
It
Monday
depends.
test.
It depends on.
Because you guys are conscientious for the most part.
Yeah, it depends on how much effort you want to put in.
Conscientious, you're good. You
You are
keep
aware.
track. Yeah,
Yeah,
you're
I
aware
know.
of your assignments and studying
Generally
on time.
speaking, I think we're being a little gracious.
I think we are too. But they're a little more aware than my earth science class.
Well,
I don't know how some people function.
you're a little taller than midgets.
Hey, not cool.
No, you didn't. You missed the point.
I don't care.
I know it depends you regardless.
Anna's not that much taller than me.
All right, so Friday will be a
Actually-
work day, but try to have some of those questions done so you can ask questions on Friday. There will be no opportunity to ask questions on Monday.